Okay, so the plan for today, we will complete the class example 12, which is class example 15 on your part. That should be class example 12. Okay, so we should complete that one, and then we will go through very quickly on some other class examples, but those are already worked out. You should have a package where I gave you 3 class examples, like class example 4.2, 4.3, and another example from the exercise. So we will go through very quickly on those. And after that, we'll be done with the mass conservation. And then we will start the second conservation principle, which is the energy conservation. Okay. And on that, we will go through the Euler's equation of motion and a little bit of Bernoillis equation. And I think up to that point, I can cover today. Okay, that's what we will do. Now you have one homework due, which is Monday. I extended the time till midnight. So you will be able to ask me question on Monday also, if you have any question. And there will be a quiz. Most probably that is quiz 6. I can't remember what will be the number. That is again the reading quiz. That will be for next week. Open book, anything. You will just go through the textbook and answer all the questions. Okay. So that is the plan for today. And okay, let's start working on that. We developed the equation for mass conservation for steady flow, because we are not doing anything with unsteady flow, right? So for steady flow, we finally came up with the expression which said that incoming flow should be equal to the outgoing flow in terms of volume, in terms of mass per unit rate of time, right? Per unit time. It can be per unit second, it can be per unit hour, anything. So for class example 12, the question was through inlet A, carbon dioxide is entering into the tank. Through B, nitrogen is entering into the tank. They are mixing up within the tank, and as a mixture, they're coming out through the outlet C, right? So we had 2 inlets, 1 outlet, and we listed all the given values, and we found out what we need to find out, which is VC. And then we started working on that. We wrote the equation, and we saw that we know the AV for A, AV for B, and rho A for C, but we don't know rho A, rho B, like the density of carbon dioxide and density of nitrogen at that pressure and temperature. So obviously, whenever you have a gas within a certain temperature and pressure, you instantly know that you need to use the ideal gas law to calculate the density, right? So that's what we did. For your class, we already did the density of carbon dioxide and density of nitrogen. Now we will start our class from here, like we will use this value here, okay? And then we will calculate the value for VC, okay? So let's do that. For this part, so what was the density for A, carbon dioxide? 4.062, okay. And the area of that one was pi 0.1 square 10, okay. Pi 0.1 square 10. And that was the A, plus the density of B is 2.585. Pi 0.15 over 2. Pi 0.15 over 2, 6, right? Equals to 1.456, 1.456 Is that the correct number? 456? 546. 546 pi 0.1 square VC. Okay. Now you need to calculate the VC. Okay. So do that. Give me the value for this whole thing, and this one, and calculate the VC. Do that. I'll be here. If you have any question, just ask me. Okay. This is the outlet. Yes. Yes. So that is the R. The radius was correct. And it's a little bit higher than that. Check the calculator. It's close, but it's not correct.
31.9. No, that's what I got. Yeah.
So if you do the calculation properly, you should get 31.9. Okay, so give me the number for this one. 4.06 pi 0.1 square 10. What is the number for that one? 1.27 or something like that. 624. Okay, plus. Say it again. 274. Are you sure this one is 1.624? That's what I think. That should be here, 1.27. I don't have the breakdown of calculation, but from section 1, I kind of know that it should be 1.27. Okay, 0.274. And what is the answer here? No, here, just 49. Okay, so the VC is 1.27 plus 0.274, 0.049. If you do the calculation properly, you should get something around this number, maybe a little bit less or more than that. And since it's a velocity in SI system, what will be the unit? Meters per second. Yes. Okay. So that was the answer for class example 12B. Now for mass conservation, you will not see that much variation in the problem. Most of the time, like anytime, either it will be gas or liquid. Obviously, those are the fluids. And for liquids and gas, anytime you can start from working this equation like inflow to outflow, because we are not doing anything unsteady in this course. So everything should be steady. So this is the equation for mass conservation all the time. Now, if you have the liquid, you can cancel rho inflow equals to rho outflow, but I recommend always start from this point so that you will not get confused. And after that, you can cancel the rho. Okay. Now, I gave you few other class examples just to do more practice here. There is no trick, no surprise, nothing. Just to do more practice, I have given you that. So class example 4.2 and 4.3, that is from your textbook. If you have that, if you prefer the color version, you can look at your textbook. You will get the colored version, but your copy is the black and white one. So here, the example 4.2 is for liquid, okay? And this is a fire extinguisher. You have two outlets, the same diameter and everything. If I say that one is outlet 1 or outlet A or B, something like that. This one is outlet 2. Most probably it's in your copy, it's A, B or something like that. So these are the outlets, and this fire hydrant is getting water from some source from the ground. So that is the inlet. So you have actually one inlet, rho AV inlet, but you have two outlets. So you need the summation of rho AV outlets, right? And you will find out the individual value, either it's given or you need to find out. Now, the thing is, since the fluid here is water, so water at density of water at inlet should be equal to the density of water at outlet, right? So you can say here, only for this case. So after that, you can work on that. Okay. So that is the class example 4.2. Now for 4.3, what is the fluid type, gas or liquid? 4.3, it's the gas, it's the airflow. So some air is entering through this way, that is the inlet, and that is going out through that way, so that is the outlet. And inside that, the heat energy is applied here, like the heat obviously will change the density of the air because that will increase the temperature. Now you have one inlet, one outlet, so you can write down PAV in, PAV out. You don't need the summation sign, but if you want, you can use that. Now, this time, since it's the air, the temperature, you can't say this one. So you need to use the density, and if the pressure and temperature is given, you need to find out that. You need to make sure that the pressure and temperature should be absolute pressure and temperature, and using ideal gas law, you can find the density if it's not given. Okay. So that is example 4.3. There is no tricks, nothing, straightforward. But the last one, there is a small trick for this one. Here, this pipe or this channel, this is the triangular channel, you can see that. Now, what is the total height of this channel? 0.5 meter. But you can see the water is not up to 0.5 meter. There is an empty space, right? So water is up to 0.4 meter. So when you calculate the area, like Q equals to AV, that A should be just the area of water, okay? Here. So you need to know what is the width. Here, I think I gave that width in your copy. So that should be the one, 0.43 or something like that. Oh, okay, 0.32. Yeah, I found that using the similar triangle, so you can do that. So the area will be what for this one? Half times base times height should be what? 0.4 or 0.5? 0.4. Yes. So that is the only trick here, that you need to calculate the proper area. Other than that, everything is same as what we did for class example 12A. Okay. So other than that, I don't think you will see any other variation of mass conservation principle. It should be within these types of problems. Okay. Now you are fully ready for your homework 7. You will see there is one example about like gas, one example about not example, like one question about gas, one question about the liquid or something. So start working on that, and if you have any question, just stop by or email me, or you can ask me on Monday. Okay, are we good? Mass conservation. For mass conservation, you will not see that much tricky question or something. It is always pretty straightforward, always mass in equals to mass out. So you should be fine. Okay. Okay. So if you don't have any question about this part, we can start our second part, which is the energy conservation. Okay. So you should have a class lecture copy for lesson 24 or 5, or what is that? Yeah. So we will use the same lecture copy for today and for Monday. So please make sure you're bringing that on Monday also. Okay. So I'm stopping sharing this one, and I will use the other one, which is the Bernoulli's equation here. Okay. So the Zoom people, can you see that screen on your computer? Okay. Here. So these are the learning objectives for today and for next class. We already did the complete class example 12. Now we will start working on the energy conservation. Now, though we said that it's we will start the energy conservation, we need to know some background of or some basis for the energy conservation. So we will discuss the Euler's equation of motion, and then we will discuss the Bernoulli's equation. I know some of you have heard about the Bernoulli's equation, right? You don't have to remember the principle, but just tell me that you heard the name. Okay, that should be enough. We will review the principle, so no problem. Okay, so the Bernoulli's equation, like Bernoulli's around mid 18th century, he stated that for a fluid particle, the total energy should be summation of some other energies. Okay, we will discuss that. So once he stated that, after few years after that, Euler's, like, he actually came up with the mathematical expression for the energy equation. So in our class, we will at first discuss the mathematical expression, and then we will discuss the actual equation. Okay. So to do that, you know, this is a fluid particle, and you know a little bit about the streamline. The streamline is a line on which every particle has a velocity adjacent to this line. That means if we have particle here, they will have the velocity adjacent to that line. Okay. Now, for any particle, we can have two directions. One is the S direction, which is along the streamline or parallel to the streamline. Okay. Not streamline. Okay, and the n direction here, which is perpendicular to the streamline. Okay, now for both of these directions, Euler mentioned, like he stated, two differential equations. So we will not go into details. I will just write down the equation because we will develop the equation based on these differential equation. Okay, so let's write down those. So the first one is a different color, dp over density, okay, plus velocity ev z equals to 0. That is the s direction. And for the n direction, it will be negative dp over dn rho g dz over dn equals to rho v square over r. Okay. So that is for the n direction. And for the s direction, we already have that. So if we do the integration of this equation, we will get the Bernoulli's equation. We will see that. Okay. So before doing that, let's review one more time what will be the pressure variation in the horizontal direction and the vertical direction. So for horizontal direction, do you remember what was the pressure variation? For there is 0, that means the pressure will be same at any point. So at point A and at point B, that should be P equals to PB, right? And for the vertical direction, again, we will work with the incompressible here. The gamma is constant. So pressure at C will be, again, the pressure at A, gamma H. For any reason, if A is at top of the surface or something, obviously PA will be the atmospheric pressure, right? But at this point, since we are working with the general expression, I will just write down PA. When we will do the calculation, we'll decide whether it will be 0 or any other number. Okay. Okay. So now we can write down the Bernoulli's equation because we reviewed the pressure variation and we know the differential form of the equation. So what he said, Bernoulli said that for any particle here, this one, the energy for that particle will be the summation of the pressure due to the the force or total what energy should be due to net pressure force for the velocity or for the kinetic energy, and it will be for the gravitational potential energy. I think you know about the potential energy, right? A little bit, maybe. So it's like if I'm holding a object here and here, obviously I'm working against the gravity. So that work is actually stored as the energy or work for this object, right? So the total energy will be equals to some constant value at any point, and it will be the summation of energy due to pressure energy due to motion plus energy due to gravity. Okay. And if we write down the mathematical form, that should be energy due to pressure should be P over gamma. It's not P over, that should be P over gamma. Okay. Energy due to motion will be V square over 2. And energy due to the gravity will be Z okay, and it will be constant. And the equation you can actually get from, like if you just integrate that equation, you will get the same equation here. Okay, and that is the Bernoulli's equation for a single point. And in our next slide, we will see how can we get the equation for, if we want to apply the equation for in between 2 points. Okay, are we good, everyone, up to this point? Okay, so let's write it down. Apply the Bernoulli's equation in between points 1 and 2. Like if that is the point 1 and that is the point 2. So for point 1, what will be the equation? P over rho, but this time P1 because we are working with point 1. V1 square over 2 and GZ1, right? Equals to P2 over rho V2 square over 2 and CZ2 and we said that it will be constant. Also, we can say this constant value is H. H is total energy head. We will discuss total energy head later, but at this point, let's just write down that it's the total energy head. Okay. Okay. Now, this is the equation for energy, right? We are discussing with different types of energy. So for each term, we should have the unit of energy, right? That's what we should have. So we have P over gamma, we have V square over 2, we have G, Z. Now tell me, what is the unit of energy in SI system? Newton meter, okay. Okay, that is the one. Or joules, yes. So Newton is for force, M is for distance, right? Okay, now if we find out the unit for each one, that should be Newton meter, right? Let's check if we get that or not. Force times distance. Okay. Okay, so what is the unit for P in SI system? Pascal or Newton over meter square, right? And for rho, it's kg times kg over meter cube, not times. Okay, so for what do we have here? Meter square, meter cube. So that means, yes, so you are having 1 meter So finally, what do we have? This one, but we should get just Newton meter, not any kg or something like that. We are having that here, right? So that is your weekend assignment. You will tell me on Monday why we are not having Newton meter, but we are having Newton meter per kg. Okay, you will tell me that. You will get the answer in your textbook. Just go through your textbook, article 5.2, you will get the answer. But I want that answer on Monday. Okay, you want to say something right now?
No, sorry.
Okay. It's pretty obvious why we are not getting that from the unit, but I want the answer on Monday. Yes.
Can I just guess right now?
Yes.
Is it a unit mass as a particle?
Kind of. So it is kind of, instead of the total energy, this equation is actually energy per what? Unit mass. That's why we are having that. I already told the answer. You actually guessed that, but good job. Yeah. So that's why we are not having just the joule, but joule per kg. That means this equation is total energy per unit mass. Okay. Okay. Good. So you will, if you do the same for the other two also, you will get the same unit, that Newton meter per kg, because it's for any equation, all the components should have the same unit, and you will see they have the same unit. Okay. Okay. So since you already answered the question, I can show you this slide. So let's go through all the points here. Can anyone read the very first one? Okay, thank you. The answer of my previous question is here, because we are always considering a unit mass of like moving fluid, and that's why the energy is also like that. Okay, so for the second one is what? Each term has units of energy or work per unit mass. I think in your copy, there is a blank space, so you need to write down on that part. What is the number 3? The equation states that the sum of the flow work associated with pressure, which is the P over gamma or P over density, kinetic energy, which is the V square over 2, and the gravitational potential energy, which is GZ, right? Okay. So in our country, we were ruled by British for 200 years. So all of the pronunciation and everything, we follow the British rule. And we pronounce Z as Z. Z, yeah. So whenever I have to say G and Z at the same time, I need to take a pause, because they are too much similar. Z and G. Okay. Okay, so the last one is has the same constant value along the streamline. What is the next sentence? Provided no friction or external heat or energy is added. That means this equation is only applicable for certain cases. Not every time you can use that. That means this equation has some limitations. Okay, so since we have a little bit time, I didn't discuss that in the section 1, but I'll discuss that here because we have all more than 12 minutes. So let's discuss the limitation of Bernoulli's equation. Okay. So from this sentence, you can kind of guess what are the limitations. We will just write down those here. The very first limitation will be what? Temperature or heat. Yeah, that can be, that means there shouldn't be any energy added or taken out from the system, right? Okay. So I listed that as number 4, but I will add that here as number 1. No, that should be no energy limitation when there is an addition. What is the opposite word for addition? Subtraction, okay. Of energy. Okay, because if you do that, you can't say that is constant anymore, right? Okay, so we did, and if you add heat, that can be one source of energy addition. Okay, from this picture, what can be the, oh, if you add some like pump or something here, that is another source of energy here. So I will just write down a little bit example here, maybe heat pump, something like that. Okay, what can be the second limitation from this picture? That is, or something like this one. Okay, so this one, it will not affect the volume, but it will make the friction. So what we can say, the Bernoillis equation, the two main condition was the fluid should be the incompressible and the inviscid. If you can't remember what was inviscid, that is actually when the viscosity is almost 0. Okay, and the incompressible is the gamma is constant. So the second one can be, we can't have this viscous friction, okay, or the fluid can't be viscous. Okay, so let's do that. When the fluid is not inviscid, okay. Oh, for the first one, you can also write down friction also, like that eddies, that will actually take out the energy from the flow also. So that is another thing, formation of okay. So we are done with this one, friction. What else we can have? From the condition, you also know that if the fluid is compressible, we can't use that equation. Okay, so that kinds of telling you that we will use this equation most of the times for liquid. Okay, so that is condition number 3. Let's use black color. When the fluid is not incompressible. Okay, and number 4 is when you have like a sudden change of the direction of the flow. Usually again there is like flow separation or something. Flow separation means this flow will be not continuous. Here there will be a large number of eddies again. So that can be the last one, when there is not a sudden changes in the flow direction. Okay. So I find this picture useful, even if you can't remember all the reasons. Whenever you look at this picture, you will know what are the different reasons for that, right? So those are the limitations of Bernoulli's equation. And whenever you have this type of scenario, you can't use the Bernoulli's equation. Okay. So in our next class, what we will do, we will discuss a little bit of Bernoulli's equations application, and then we will move to the energy equation. Energy equation can overcome these limitations. Like energy equation can be applicable for any cases because that is a broad equation. Okay, so that's what we will do. I will just stop here, and you all have a good weekend. I will